Hi everyone, and welcome back to Physics 2A lecture. Today we'll be going over an introduction to physics, and I'll start by talking about what science is. So science is going to encompass a lot of different theories and laws that are general truths about nature, okay? And really a body of knowledge that they encompass. So we have some different ones, including physics, of course, that's what we're studying, biology, we have geology, we have chemistry, astronomy, and then we have, deeper fields in between all of them, okay? And what we are looking at in particular is physics, okay? And that's gonna describe phenomena in nature, okay? And that describes the interaction between energy, matter, space, and time, okay? And what physics does is it explains the fundamental mechanisms that underlie every phenomena in nature, okay? Now, physics is also used, it's really used to understand the function of everything in the world and now outside of the world. Okay, so we use physics in all kinds of different areas of science because it's really the baseline, okay? All right, so the first thing I want to do is talk about the scientific method, and that starts out with basic observations, which lead to hypotheses and an experiment, okay? So let's take something that we do every day, okay? So let's say I'm walking down the street and I see a leaf. Okay, and that is going to be my observation. My observation is there is a leaf on the ground, okay? My hypothesis then is going to be, answering where did that leaf come from? So I can say the leaf came from that tree over there, okay? That would be my hypothesis, okay? Now my experiment is going to be to go to that tree and determine if it did indeed come from there, okay? So in physics and in a lot of other sciences, we need some kind of mathematic theory and be able to test that experiment multiple times. So if we don't have a mathematic theory behind the idea, we may not be able to actually test it, okay? So that's very important. We also need to be able to explain our science to others. If we can't communicate our science, what really good is it if only you can understand it? Okay, so you need to be able to express to others what you found, okay? Now, I want to go into our units, a little bit of trigonometry and vectors, okay? And I'll probably cut this up a little bit because this might be a little bit long, okay? So first things first is units, okay? Units are very, very important, okay? They describe a physical quantity. Let me give you guys an example. Say you want to go to the store and you're saying, oh, it's 20 that way. What? 20 what? 20 what that way? It could be 20 minutes that way. It could be 20 miles that way. 20 seconds that way. 20 cups that way. Oh, you can't see it. We have no idea what you mean by it's 20 that way unless you tell us the units. Okay, so things that could make absolutely no sense unless you put your units. Okay, so units are very, very, very important. Okay, and I'll stress this the entire semester. Now in science, we use the metric system, okay? And opposed to our US system, not really 100% sure, but we use a lot of, miles, inches, what else? Miles, inches, feet, things like that. But in the metric system, it's a lot easier because we go by powers of 10, okay? Now, let me show you what I mean. So first I need to turn my little pin on. A second here. Okay, so in our metric system, we typically look at length in meters. Oops. Okay, so we're going to be looking at length in meters, and we will be looking at our mass, which is not the same as weight. Okay, and we'll talk about it a little bit later in the semester in a few lectures. But it is a quantity of matter, and we look at mass typically in kilograms. Okay, and with time, we typically look at it in seconds. Okay, now I have a little table here to kind of show you what some of the different prefixes mean. Okay, so I say meters, okay, but what if I say kilometers? Say I'm in Europe traveling somewhere, you know, because we can totally do that right now with the pandemic. Kilometers, it would be, you know, driving around, they'd say, oh, it's, you know, 3 kilometers that way. Well, I'm in the US and I'm used to seeing miles, but okay. But we can at least relate it to meters, which we might be a little bit more comfortable with. Okay, so if we look at our little chart here, kilo is what I'm looking for because it's kilometers. So kilo is our prefix here, okay? Oh, and you can see our symbol is K. All right, so our meaning is going to be 1,000 or 10 to the third. Okay, what do you mean by that? Well, 1 kilometer then means 1,000 meters, okay? Or 10 to the 3 meters, okay? So that's what the kilo and kilometers means, okay? Now, we can say the same thing for mass, okay? So we typically use kilograms, but we could talk about it in terms of grams, and it would be the same sort of thing, okay? It would be 1,000 grams, okay? Now, we can also do this with other lengths, like we're used to centimeters, okay? Centimeters, okay? It says that 1 centimeter or centimeter would be 0.01 meters. Okay, that's what that would mean. Or we could switch that around doing some multiplication and such. We can say that 100 centimeters is equal to 1 meter. Excuse me, sorry. All right, and so forth. So this will be super useful. You can always, you know, find this elsewhere, but this is a pretty good one that I found. Okay, so this is our metric system, basic units. Now, let's go to our derived units. So those units that we were just looking at, these are like known, somebody measured it and we're like, okay, this we're gonna define as 1 meter and so forth, okay? Now these are derived from those other units. Okay, so as you hopefully know how to calculate an area, it's gonna be length times width. Okay, easy, right? So say we have this rectangle here, we have some length and some width, okay? And that'll make up our area. Now, what am I asking for derived units? Well, if I'm multiplying a length times a width, what are my units gonna be? Well, if you think about it, our length and our width are both gonna be in meters. So for the units, it would be meters times meters, which is gonna be meters squared. Okay, so for our area, our derived units is gonna be meters squared, okay? Now for volume, it's gonna be something pretty similar, okay? We have our length, we have our width, but now we have some kind of depth, okay? So we have our length times width times depth, which is gonna be meters times meters times meters, okay? And that's gonna give us a meters cubed, okay? So that's gonna be our derived units for volume, okay? All right, so moving on, we have velocity and acceleration. Now, our velocity, we're really gonna just look at it as speed right now. So I should probably write speed instead, okay? We wanna be careful with that. So we know our speed is some distance divided by time, right? Because think about it this way, if you're driving down the highway and you're going 55 miles per hour, that's your distance divided by your time, okay? So our distance in that case would be miles, but in our metric units, we want to say meters, okay? And in time, instead of hours, we should write seconds, okay? This is gonna be standard, okay, for this course. So that will be our derived units, okay? Now we have acceleration, which is gonna be our rate of change of velocity, okay? So how fast is he changing, okay? So acceleration is going to be our distance over our time, and it's gonna be a rate of that. So it's gonna be a distance over time, okay? So if we're just looking at our units, our distance is gonna be meters, and our time is gonna be in seconds, and we have a seconds times a second, so that's gonna be seconds squared, okay? And now that is our derived units for acceleration, okay? Now I know that was quite a bit to take in right now, so if you want to, you know, cool down, take a little bit of a break, this would probably be a pretty good stopping point. If not, let's chug ahead. I know this is a lot of information at once, so bear with me. Okay. Now, I'm gonna do some examples of unit conversions. Okay, so one thing we want to do is be able to convert between different units. Like, let's say we are in, you know, Europe or something, and they're saying, oh, it's blah, blah, blah kilometers, it's blah, blah, blah kilometers. And we're just thinking to ourselves, what in the heck are they saying? I don't understand how, like, far is a kilometer. That could be, you know, 200 miles for all I know, you know? So I don't want to just go with it. So unit conversions are very important for this kind of scenario. So let's say that someone tells us that it's going to be 2 kilometers ahead. Okay, well, let's convert that to miles because I don't know how far that is really, okay? So what we'll do is we'll go over to our unit conversions right here and try to find miles to kilometers or kilometers to miles, whichever. Okay, so I see this first one here. We have kilometers to miles. Okay, so what we'll do is, some people may have heard of this as the train track method. I just use it as straight multiplication. Okay, so what I'll do is I'll write it down in both ways. So this is the way that I usually do it. So we have 2 kilometers. We want to convert to miles. So I'm going to put that 1 mile up top and then divided by our conversion. So that's going to be 1.609 kilometers. Okay, so the train track method, I believe, goes like this. It's very similar, just looks a little different. 9 kilometers, okay. And the train track method, as you can see, there's a multiplication here. That's what this line is supposed to represent. And then this line, when you see that line, it represents division, okay. So these are the same thing. If you've seen it that way, that's fine to use it that way as well, whichever works for you. Okay, so now I can say, okay, I can multiply across the top. So 2 times 1 is 2, right? Divide the bottom, that 1.609, okay? And then I look at my units. So my units up top is kilometers, miles, and then dividing by kilometers. So my kilometers cancel in both cases, okay? So we're left with miles, which is good because that's what we want to know. We want to know how many miles are in that 2 kilometers, okay? So now we take out a scientific calculator and we say 2 divided by 1.609 equals, and we get 1.24 miles, okay? So it's about 1.25 miles that we would have to walk or drive to, whichever we're doing in Europe. I wish we could go to Europe. Not really, not right now anyway. Okay, anyway, sorry, a little sidetrack there. So that is my first little example of unit conversions. Okay, so it can get tricky really quickly. Okay, I'm going to show you another example, but let me first clear the screen because I think this one is going to get a little bit messy. Nope, that's not what I want to do. Okay, come on. Sorry, I have this new little pen and pad so I can actually, you know, write on the PowerPoint, and it can be tricky. I'm still learning, so there's definitely a learning curve on this guy. Okay. Oh, see? What? Oh, give me just a second. Pen. Okay. So let's go with another example. Let's say we want to travel, we need to go 20 miles. We need to go 20 miles, okay? But we only have, let's see, how much time do we have? We're gonna have 15 minutes to get there, okay? Now, if we only have 15 minutes to get there, we need to know, are we actually gonna make it, okay? And how fast do we need to go, okay? So, remember when we're looking at speed, or B here, speed is going to be our distance over our time, okay? So we have our 20 miles over our 15 minutes, okay? Because it's distance over time, right? Okay, well, if I get some answer from this, you know, if I divide it, I'm gonna get something that's in miles per minute. Does that really mean much to us? Not really, because we look at everything in miles per hour, right? So why don't I first convert our 15 minutes into hours, okay? So let me take my 15 minutes and I wanna convert it to hours. So I'm gonna look at my little conversions over here and see how many minutes are in an hour. Hopefully, you know, we know this offhand, but sometimes it takes us a minute. So I'm gonna see right here that it takes, for 1 hour, there are 60 minutes. Okay, so what I will do now is multiply across the top. So I get 15, divided by the bottom, 60, okay? And our minutes cross out and we are left with hours. Okay, now I will divide that. 15 divided by 60. It's going to be 0.25 hours, which makes sense because 15 minutes is a quarter of an hour, right? Okay, so now we have our time in hours. Now we can figure out our speed. How fast do we need to go? Okay, so again, we're going to take our distance, 20 miles, and divide it by our time, 0.25 hours. Okay, and so if we do that, 20 divided by 0.25, we get 80 miles per hour. Okay, now 80 miles per hour, that is really fast. We're probably not going to make it on time, but that's okay. Better safe than sorry. Okay, so these are the kind of unit conversions that you'll be using throughout the course. Maybe, you know, we'll add to this list later on, but for now, this should be okay. Okay. All right, moving on to coordinate systems. Now, coordinate systems, you've probably seen the typical Cartesian coordinates before, the X and Y axes, like here, okay? But you may not have seen polar coordinates, or you may have. Hopefully you guys know a tiny bit of trigonometry, but if not, that's okay, because we're gonna go over it in a minute too. Okay, so our first one, as you can see, is our y-axis here and our x-axis. Our polar coordinates are going to be a little bit different. So yes, we still see the x and y axes, okay, but now we are more concerned with our r, which is our radius, okay, so how long this line is here, and theta. And theta is going to be this angle here, okay, between the x-axis and that length r, okay? So moving on to our trigonometry. So I have the same picture here, okay? And we're gonna analyze it a little bit. So first things first, we want to know is our Pythagorean theorem, okay? So that is when we have a right triangle like we have here, okay? We know that our a squared, which is, say it's this side, is a, plus b squared, which would be like here, which would be here. Okay, so that's our b. And then equals c squared. Okay, so we have our a squared plus b squared equals that c squared, this longer side. Okay, so let's see here. All right. So what we want to go over is remembering this, these trigonomic identities, okay? We say so katoa, okay? So the first one is gonna be so, okay? And we are gonna say that it's sine theta equals our opposite over hypotenuse. So S is for sine, O is for opposite, H is for hypotenuse. Okay, and I have this here for our example. So it's going to be our opposite, which is going to be Y, over our hypotenuse, which is R. That long side is going to be our hypotenuse. Okay, let me erase this. Okay. All right, so we know our so, what that stands for. What about ca? Ca is going to be our cosine equals our adjacent over hypotenuse. Okay, and there's our example here. We have our adjacent, which is going to be this guy here, x, over our hypotenuse, r. Again, that longer side. Okay, and now we can do TOA. TOA is tangent theta equals opposite divided by adjacent. Okay, and again, we can see our example here. We have opposite, boom, is y over adjacent x. Okay, so hopefully this kind of sparks some memories, hopefully good ones. Now, we want to remember that we may not always have this exact orientation of our theta. So let me give you guys another example. Let's see. Let me erase some of this and then I can use the same thing here. All right. This pen, man. Okay. All right. So let's, instead of looking at our theta here, let's draw another angle here. And we will call it angle, let's see. We'll call it beta. Okay, it just looks like a funny B. Okay, so now we're looking at a different angle. Okay, so say we want to analyze that. So we want to do the exact same thing. So we're going to say our sine beta is going to be our opposite. Okay, so opposite is going to be x. Okay, over our hypotenuse, which is now, which is still r. Okay, so notice the difference here. Now that we're looking at a different angle, our opposite and adjacent definitions are going to be different. Okay, so watch out for that. Okay, so now let's do our cosine. So cosine beta, it's going to be adjacent, which is going to be y, over our hypotenuse, okay, which is going to be r. Okay, so last one, tan of beta is going to be adjacent, or I'm sorry, opposite, opposite, which is x, over our adjacent, which is y. Okay, so again, watch out for your angles that you're looking for. It all depends on that angle and where your right angle is in your triangle. Okay, so watch out for that. All right, and the last thing I want to talk about are some physical quantities that we will be looking at. Okay, so I didn't really mention it earlier, but we have two main ones that we'll be looking at, and it's going to be scalars and vectors. Okay, scalars are going to be anything that has a magnitude to it. Okay, so like 10 cups. Okay, things, I don't know, 10 computers, things like that. Okay, it just has a magnitude, a number. So we have some examples here that we use in physics. Okay, mass. Okay, mass is going to be measured again in kilograms typically for us. And that's going to be a scalar. It's just a magnitude. Same thing with temperature, just a magnitude. It's a number. Speed, same thing. I talked about, I was going to talk about velocity, but then I changed it to speed. That's exactly because of these definitions here. Scalar. Okay, just a magnitude, just meters per second. Okay, now with vectors, vectors have that same magnitude, but now they have a direction as well. And the main one that we're going to be looking at is going to be velocity. Okay, so the difference between velocity and speed is that velocity has a direction. Okay, so we not only have our previous units, meters per second, but now we also have a direction, say east, okay? So if you think about the difference, I mean, you can't really say mass is gonna be, 10 kilograms east. That doesn't make any sense, right? But this does, our velocity, if we're going, 30 miles per hour west, it makes sense to have a direction on it. But just given the speed, it tells you how fast you're going. But when you add that direction, it kind of helps a little, I guess you could say. So we will be looking more in depth into that in our next lecture. Okay? And just stay tuned for other posts. All right?